Hello, my dear mechanical and civil engineers. This is Chandrasekhar welcoming you all to this wonderful Ground Zero series. In this series, we bring the most important concept in the most interesting manner through the animation so that it becomes easier for the students to understand those concepts. So, in today's discussion, I will be talking about the very well known Bernoulli equation from the subject of fluid mechanics. So in this topic, we will be discussing about the derivation of the Bernoulli equation through Euler equation by applying the Newton's second law. Along with that, I will also talk about the various assumptions which are to be used to apply the Bernoulli equation in mathematical problems, and we will also talk about the physical significance along with the practical examples of Bernoulli equation. So before I start, let me quickly introduce myself. My name is Chandrasekhar, mechanical engineering graduate from IIT Delhi, having more than 10 years of teaching experience in the field of GATE, IES and PSUs. You can connect with me through the mail ID which is there on the top of the screen, and you can also join me on the Telegram, that is Mechanical by Chandrasekhar, and the link is also mentioned on the bottom of the screen. So let us start discussing about the Bernoulli equation. So Bernoulli equation is actually the part of the fluid dynamics. Fluid dynamics is the analysis of the flowing fluid considering the various forces causing the motion. So the major forces which cause the motion are, one of them is the pressure force which acts normal and compressive. The next one is the gravity force which is always acting in downward direction, that is the weight of the fluid. When we consider these two forces in our analysis, the equation obtained is called as Euler equation. The next major force causing the fluid motion is the viscous, shear or the tangential force which is developed due to viscosity of the fluid, which is always acting tangential to the fluid. When all these three forces are taken into consideration, then the equation obtained is called as Navier-Stokes equation. And another important force is the force of turbulence, that is due to mixing of the fluid particles during the flow. So when all these forces are taken into consideration along with the tangential turbulence force, then the equation obtained is called as Reynolds equation. Then we obtain the Reynolds equation. So we will have our discussion starting with the Euler equation, and from the Euler equation we will try to develop the expression for the Bernoulli equation. So let us talk about the Euler equation. In Euler equation, the two assumptions are taken into consideration. One is the flow must be non-viscous, or we can say the viscous force must be zero. Other than that, the flow must be steady. The fluid behavior during the flow should not change with time. In these two assumptions, if we analyze the fluid flowing along a streamline, if there is a flow along the streamline, and for our analysis, if we take a cylindrical fluid element of length dA, the length ds, and the area dA. If we take a cylindrical fluid element along the streamline, that is dA by ds, so the two forces which we are supposed to consider in this analysis is pressure force and gravity force. So on the left of the fluid element, the pressure force is acting normal and compressive, that is in the direction of flow. If the pressure is assumed to be P multiplied by dA will give you the pressure force which will be acting in the direction of the flow. And on the other side of the element, the pressure force will be acting in the direction opposite to the flow. Let me call this pressure to be P dash multiplied by the area dA. These are the pressure forces acting on this fluid element. So P dash can be written by using the Taylor theorem expansion, that is P plus del P by del S into ds when higher order terms are ignored. And other than these two pressure forces, the another force which is acting on this fluid element is the gravity force, which is acting in downward direction, that is weight of the fluid element. If we assume this angle to be theta, and if we apply Newton's second law on the fluid element, what is Newton's second law? According to Newton's second law, net force exerted on the fluid element is equal to mass of the fluid element into acceleration. As the Newton's second law is a vector equation, we need to specify the direction for applying this Newton's second law, and the direction specified is tangential or the flow direction or along the streamline. If we apply this Newton's second law along the streamline, the weight will also have a component in the direction of the flow, and the right hand side will be mass into acceleration. Because the flow is steady, local acceleration will not be there. Temporal acceleration will be zero, local acceleration will be zero, only convective acceleration will come into picture. So if we write the mathematical expression for Newton's second law along the flow direction, along the tangential direction, then we will obtain the expression for the Euler equation, or the differential equation, differential form of Euler equation, that is del P by rho plus V into dV plus G into dz will be equal to 0. And if we integrate this equation, then we obtain the integral form of this Euler equation. So integration of dP by rho plus integration of V dV, that is V square by 2, plus integration of G into dz, that is equal to gz, is equal to constant. This is the integration form of the Euler equation. P represents the pressure of the fluid, Z is the vertical distance from a reference line, and V is known as the velocity of the flow. Rho is the density. Because we have not considered the flow to be incompressible in this expression, that is why we obtain the Euler equation. But if we assume the flow to be incompressible as well, it means the density will be constant. Density will not be a function of space and time. So the first term of the Euler equation, density can be taken outside the integration, and integration of dP will be equal to P. So this is the assumption to be applied other than the non-viscous and steady nature of the flow, and we get the equation which is very well known, that is called as Bernoulli equation. So according to Bernoulli equation, the first term of the expression represents the pressure energy of the fluid, the second term represents the kinetic energy of the fluid, and the third term represents the potential energy of the fluid. So it is the sum of total energy of the fluid which will remain constant. So each and every term represents energy per unit mass of the fluid element or mass of the fluid. So the unit is joule per kg for each and every term here. So this represents the Bernoulli equation. So we can comfortably say about the Bernoulli equation that in case of ideal flow, when the flow is said to be ideal, when it is non-viscous, viscous forces are not existing, or there are no relative motion between the adjacent fluid particles during the flow. The flow must be steady. The fluid behavior during the flow does not change with time, as well as the flow is incompressible. That is, the density of the fluid does not change with space and time. So for an ideal flow, the total hydraulic or the mechanical energy of the fluid always remains constant. So the physical significance of this equation is, the Bernoulli equation is nothing but the energy conservation equation for an ideal flow. The total energy of the fluid always remains constant when the flow is ideal, or when the fluid flow satisfies all the given assumptions. So that is one form of Bernoulli equation. If we multiply whole equation with density rho, because rho is a constant parameter, rho is constant. If we multiply whole equation with rho, then we will get another way of representing the Bernoulli equation. That is P plus rho v square by 2 plus rho gz, or we can call it as rho gh, is equal to constant. So each and every term represents energy per unit volume. Energy per unit volume. And energy per unit volume is nothing but Newton per meter square or Pascal. So each and every term of the Bernoulli equation, this is the second way of representing the same Bernoulli equation by multiplying the previous equation with rho. So first term represents the static pressure of the fluid, P. It can be absolute pressure or it can be taken as gauge pressure. Static pressure of the fluid, that represents the pressure energy of the fluid. The second term represents the dynamic pressure of the fluid, the pressure which is developed due to velocity of the fluid, that is the dynamic pressure of the fluid. So if we combine the static pressure and dynamic pressure, we obtain the stagnation pressure of the fluid. The sum of first and second term represents the stagnation pressure of the fluid, and the third term represents the hydrostatic pressure of the fluid. According to hydrostatic law, P is equal to rho gz. So Z is the vertical height, vertical distance from a reference line, V is the velocity of the fluid, and P is the static pressure of the fluid. That is another way of representing the Bernoulli equation. And if we divide the whole expression with rho g, then we obtain another way or another form of Bernoulli equation that is most frequently used in our analysis. The first term will become P by rho g, that is called as static pressure head of the fluid. Why it is static pressure head? Each and every term now represents energy per unit weight. And energy per unit weight means joule per Newton. And joule is Newton into meter. Divide by Newton will give rise to meter. So each and every term now represents the head of the fluid. First term represents the static pressure head. It can be absolute or it can be gauge. The second term of the Bernoulli equation represents the kinetic energy head, velocity head, or we can also call it as dynamic pressure head, V square by 2g. And the third term Z represents the hydrostatic head, or we can call it as datum head, elevation head, or we can also call it as potential energy head. So sum of these three heads for a flowing fluid, if the flow is ideal, then it will remain constant, and that represents the total energy head of the fluid. All right. So how to apply this Bernoulli equation in our problems, in our numericals? Let us discuss about that. But before that, let me talk about the assumptions which are important, which must be taken care before applying the Bernoulli equation. One of the assumptions I have already mentioned, the flow must be non-viscous, or we can call it as inviscid flow, or we can also call it as frictionless flow when there is no relative motion between the adjacent fluid particle. Viscous force is 0. The second assumption is the flow must be steady. The fluid behavior does not change with time. The third assumption is incompressible flow. The density of the fluid does not change with space and time. And along with that, there should not be any other form of energy transfer to the fluid or from the fluid. So that is, there is no heat and work transfer. And last but not the least, the assumption is the flow or the equation, Newton's second law, is applied along the streamline. That is why we have taken the acceleration to be tangential one. So once we apply all these assumptions, or we have all these assumptions in the flowing fluid, then we can write the Bernoulli equation. And three forms of Bernoulli equation I have discussed with you. The first term, first expression, energy per unit mass. The second expression of the Bernoulli equation, energy per unit volume. And the third expression of the Bernoulli equation is energy per unit weight, or in terms of head of the flowing fluids. All right. So how to apply this equation in case of numericals? So if the flow is assumed to be ideal, when all the given assumptions are taken care, then we can say there is no losses during the flow. There is no energy loss in the flow direction when the flow is assumed to be ideal. So when it is ideal, if the fluid is flowing from section 1 to section 2, section 1 to section 2, and the flow is assumed to be ideal, there is no energy loss, no losses, then we can say total energy at 1 will be equal to total energy at 2. Total hydraulic energy of the fluid at section 1 should be equal to total hydraulic energy of the fluid at section 2. This is our reference line to calculate the potential energy head. So the height of point 1 from the reference line is Z1, potential energy head at 1, and the height of point 2 from the same reference line is Z2. So Z1 and Z2 are the vertical distances from the reference line. P1 is the static pressure of the fluid at inlet at section 1. It can be absolute, it can be gauge. So if we are using P1 to be absolute pressure, then P2 should also be taken as the absolute pressure. If P1 is taken as the gauge pressure of the fluid, so P2 should also be taken as the gauge pressure. V1 is the fluid velocity at section 1 and V2 is the fluid velocity at section 2. So we can comfortably apply the Bernoulli equation in terms of head. If we write the Bernoulli equation, then this will be the mathematical expression. P1 by rho g, that is static pressure head at 1, plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Any of the unknown can be calculated from the given equation, that is the Bernoulli equation, when the flow is ideal. But in reality, the fluid flows are not ideal. Ideal flow is a hypothetical case. So in case of real flow, when the flow is real, it means there are always energy losses taking place in the direction of the flow. So in the flow direction, if it is a real flow from 1 to 2, from section 1 to 2, so there is energy loss in the flow direction. The losses are always taking place in the direction of the flow. So if the flow is from section 1 to section 2, then the total hydraulic energy of the fluid at section 1 is greater than the total hydraulic energy of the fluid at section 2. E1 will definitely be greater than E2. So in equation form, we need to add some energy loss to term 2, and that will make it a equation. So the total energy at section 1 is equal to total energy at section 2 plus energy loss from 1 to 2, from the section 1 to section 2. And in terms of head, if we write the energy conservation equation, this is not a Bernoulli equation, we call it as energy conservation equation. If we write in terms of head, so the total energy head at section 1, Z1 plus P1 by rho g plus V1 square by 2g is equal to total energy head at 2 plus the energy head loss HL from the section 1 to section 2. All right. So we can say in case of real flow, there is always energy loss taking place in the flow direction, or we can say the fluid flow always takes place in the direction of decreasing total hydraulic energy of the fluid. If the flow is from 2 to 1, then the total energy of the fluid at section 2 is greater than the total energy at section 1. So the energy conservation equation will be written as E2 is equal to E1 plus energy losses from 2 to 1. All right. So if we know the energy at 2 points, we can always find out the direction of the flow. If we know the flow direction, then we can write the energy equation with the losses term in the right direction. All right. So let us discuss some practical examples of Bernoulli principle. As I mentioned that the total hydraulic energy of the fluid, when the flow is ideal, then the total hydraulic energy of the fluid always remains constant. So if the potential energy is constant, let us say, so in that case, by increasing the kinetic energy of the fluid, the pressure energy of the fluid always decreases. That is called as Bernoulli principle, or vice versa. If we decrease the kinetic energy of the fluid by any means, then the pressure of the fluid will increase to have the total energy of the fluid to be constant. So these are some of the examples. In case of hand operated spray, when we push the plunger, then the air velocity gets increased. Air velocity, due to pushing the plunger, the air velocity gets increased, and due to which there is a decrease in pressure. And the pressure inside the bottle is atmospheric, which is greater, which is more. Atmospheric pressure is more than the outside pressure, and due to this difference in pressure, the fluid in the bottle rises to the top of the tube because of the pressure difference. Similarly, in case of aeroplane wing, the air velocity on the top of the wing, the shape of the wing is such that the air velocity at the top is high, so that will give rise to low pressure, and at the bottom of the wing, the velocity of air is low, that will give rise to high pressure. So due to the pressure difference on both sides of the aeroplane wing, there is an upward force exerted on the wing that is known as lift force. Similarly, in a ping pong ball also, if you increase the velocity, then the pressure gets decreased. And here the pressure is high, outside the pressure is high, so it will be in equilibrium. The ping pong ball will be in equilibrium. Couple of more examples based on the same principle, Bernoulli principle. During high winds, always the roof of the house move in upward direction. The reason being, due to high velocity, the pressure at 1 will be low, P1 will be low, and P2 will be high. So there is a force, lift force developed due to high pressure, due to the pressure difference from high pressure to lower pressure. If we blow air over the paper, we are increasing the velocity, so that will decrease the pressure of the fluid. That is the Bernoulli principle. The pressure at the bottom is more, so the motion of the paper will be in upward direction rather than in the downward direction. If we blow the same air between two balloons, the pressure decreases, and due to decrease in pressure, the balloon motion will be towards each other from high pressure to low pressure. So that is all about the Bernoulli equation. So we have used the Bernoulli equation for the given assumption if the flow is steady, incompressible, and non-viscous. This is the basic assumption. There should not be any viscous forces. So in case of steady, incompressible, and non-viscous flow, this is our expression for the Bernoulli equation. This was the first equation I had mentioned. P by rho, the energy per unit mass, pressure energy per unit mass, kinetic energy per unit mass, plus potential energy per unit mass, when the flow is steady and incompressible. But if the flow is steady but compressible, in case of compressible flow, rho will not be constant. In case of incompressible flow, density will be constant. But whenever we apply the same expressions for steady and compressible flow, then the expression will be modified to this. The first term will get changed. It will be integration of dP by rho, that is known as Euler equation, right? And if the flow is unsteady and compressible, compressible flow, rho is not constant. And if the flow is unsteady, it means local acceleration will also come into picture. Other than the convective acceleration, local acceleration will also be there. This expression represents the convective acceleration. And this term del V by del T is the local acceleration due to unsteady nature of the flow. This is the local acceleration. And because of the compressible nature of the flow, integration of del P by rho will also be there, and the right hand side will be constant. Now, because we have applied the force balance or Newton's second law in the direction of flow or along the streamline, that is why we have written the tangential acceleration, local plus convective sometimes. In this case, local plus convective, but otherwise for a steady nature of the flow, it is only the convective acceleration. But if we apply the Newton's second law or the force balance in normal direction across the streamline, if we apply the force balance across the streamline in normal direction, the normal acceleration will come into picture rather than the tangential acceleration. V square by R is called as normal acceleration. That is also known as centripetal acceleration, v square by r. P by rho plus v square integration of v square by r into dn. Dn is the element or the distance in normal direction plus gz is equal to constant. This is our Newton's second law applied across the streamline. I hope you have enjoyed the session. You have understood the minute details about the Bernoulli equation. So that is all from my side. Thank you, enjoy and take care.